In this part of the Neurocomputers and Deep Learning course related to training feedforward neural networks, you will learn backpropagation algorithm for a single layer perceptron. For the backpropagation algorithm, first we will consider single layer network. Consider a single layer multiple output network as shown in this figure. Here we still have n inputs denoted by uj, u1, u2, uj up to un. J is from 1 to n. And additionally we have u0 here which is set to 1. But n processing elements whose activation and outputs are denoted as activation I here and xi outputs xi, I is from 1 up to m respectively. Wji is used to denote the strength of the connection from the jth input to ith processing element. So Wji is the connection weight between input uj and neuron xi. In vector notation, Wji is the jth component of the vector wi. Here we have vector wi, it is the connection weight vector of the unit I, and the jth component is this one. In vector notation, Wji is the jth component of the weight vector wi, while uj is the jth component of the input vector u, uj is the jth component of the input vector u. Let vector uk and yk to represent the kth input sample and the corresponding desired output vector respectively. This is the kth sample and this is the desired output vector. Let the error observed at the output I when uk is applied at the input be. Epsilon ik, the error here, is the desired output at that neuron. This is the ith component of the desired output yk minus the actual output here. It is the ith component of the output when the uk is applied at input. If the error is to be written in terms of the input vector uk and the weights wi, then we obtain, instead of xik here, we are writing the output function f applied on the activation of the neuron I, which is equal to weight vector of that neuron transpose multiplied by input vector. And this is equal to desired output minus actual output for this neuron. If we take the partial derivative of the error at the ith output with respect to wji by applying the chain rule instead of the partial derivative of the error with respect to wji, we write first the partial derivative of the error with respect to the output and then partial derivative of the output with respect to the connection weight, where this first part, the partial derivative of the error with respect to output is equal to minus 1. Consider the definition of the error. If we find partial derivative with respect to output, then we have minus 1. And if we consider the second one, the partial derivative of the output of the neuron with respect to connection weight wji is equal to, this is f applied on the activation, and activation is weight vector multiplied by the input vector. Because of that, we will have here the derivative of the output function at activation I when the input k is applied multiplied by the input. Then if we insert these two in the formula, we obtain minus 1 comes from there, minus, and instead of this one, we have f prime aik and UJK. If we define the total output error for input UK as the sum of the square of the errors at each neuron output, that is, the total error is defined as 1/2 summation I from 1 up to m and square of the error at the ith output. When UK is applied at the input, then partial derivative of the total error with respect to WJI when UK is applied at the input can be written as the partial derivative of the total error with respect to WJI is equal to the partial derivative of the total error with respect to epsilon ik and the partial derivative epsilon ik with respect to WJI. So here again we are applying the chain rule. The partial derivative of the error at ith output with respect to WJI was derived previously as minus f prime aik ujk, and here for partial derivative of the total error with respect to epsilon ik, we have to consider only the term for I, and here we have a square, it cancels with 1/2, then comes only epsilon ik as a multiplier here. So this is the result we obtained when we applied the chain rule. By defining the error term delta ik at the output I when UK is applied at the input is equal to epsilon error ik multiplied by f prime ak. Then if we consider the previous formula here, we are replacing this part with the error term. So we are obtaining the partial derivative of the total error with respect to WJI is equal to minus the error term defined here multiplied by the jth component of the input k. For the error to be minimum, the gradient of the total error should be equal to 0 vector, where 0 is the vector having n times m entries, each having value 0. In other words, it should be satisfied the partial derivative of the total error when input UK is applied with respect to WJI is equal to 0 for j from 1 up to n and I is from 1 up to m. In order to reach the minimum of the total error, without solving the above equation, we apply the delta rule in the same way explained for the steepest descent algorithm. We are going in the direction of the negative of the gradient in order to decrease the error. The value of the weight vector at time t plus 1 is equal to weight vector at time t minus eta, the gradient of the error, in which WJI at t plus 1, we are considering the ji component of the weight vector at time t plus 1 is equal to WJI at t minus the learning rate eta, and this is the partial derivative of the total error with respect to WJI, with respect to this component. That is, WJI t plus 1 is equal to WJI t plus eta, the error term, and UJK. J is from 1 up to n, and I is from 1 up to n.